Hey guys, good day, good day. So, this is sort of like, it is actually, not sort of. It is a continuation of what we learned last time. Okay, last time I guess we were talking about delta G, which is Gibbs free energy at S ATP. And we said that if delta G is calculated to be less than 0, which means delta G is a negative number, that the reaction is going to be spontaneous, that this reaction will have no problem going to completion without any catalysts or sparks or heat and stuff like that, because, hey, as I said, what it is spontaneous. Okay? Like, for example, very quick example, like if you take iron and you react it with acid, that's going to be spontaneous. That's going to be spontaneous. Okay? Where you're going to be producing hydrogen gas. That's going to happen. Okay? With ease. However, if delta G was greater than 0, which means if delta G is a positive number, now the reaction is not going to be spontaneous, and it will require some more work for this reaction to occur. So that's what we learned last time. That's what we were able to find out. Okay? Doing calculation based on delta H and based on calculation of delta S. Okay? And an equation that we saw, delta G is equal to delta H minus temperature times delta S. Okay? So the equation is temperature dependent, obviously. The higher the temperature, you can pretty much expect the fact that you're going to get, the chances of getting a negative number for delta G is going to be a lot higher. That's just the way it is. So, let's talk about Gibbs free energy. I'm not sure why there were so many of the same page. That was weird. All right. In this lesson, 17.1.2, does Gibbs free energy relate to the equilibrium constant? Okay. Well, let's find out. I'm sure what you've known by now about how delta G is spontaneous and stuff like that, you probably can figure it out that, you know what? That kind of relates to what we were talking about in equilibrium constants. So let's have a little description here. As we already mentioned, that delta G, okay, describes if the reaction is spontaneous or not, and of course is temperature dependent, as we saw with the equation that I just presented to you. Let me just present that to you one more time. Okay, delta G is equal to delta H minus T times delta S. Okay, you can see, as I said, that if this number gets bigger and bigger and bigger, there's of course more chances of this being a negative number. When this is a negative number, the reaction is going to proceed. Right? It's going to proceed. Now, that's not surprising, because when you're trying to do a reaction under, hotter condition, the reaction is going to happen. Okay? Would you form more products? Well, let's see. Because will it form more product will be dictated by what this is. So what is this? Well, this is equilibrium constant. And this indicates if the reaction favors either product or reactants. Now, how do we know it favors product? It's pretty simple. If K is, greater than 1. Okay, how do you know if it favors reactant? Well, when it's less than 1. Remember, equilibrium expression? If the numerator is a smaller number than the denominator, that means you're going to have less product than reactants. Obviously, this favors reactant. Hopefully you remember that. So let's take a look at the two. Do they relate? And the answer is absolutely. Take a look at this chart. If your equilibrium constant is equal to 1, what that means is that the forward reaction basically equals the reverse reaction, because Kc is equal to the concentration of product over the concentration of reactant. The only time that this is going to equal to 1 is when the concentration of product and the concentration of reactant is the same number, right? If they're the same number, Kc is going to equal to 1. That means at equilibrium, okay, so the reaction is at equilibrium, neither reactants or product will be favored. When this happens, delta G is said to be at 0 because the reaction is at equilibrium. The forward reaction equal the backward reaction. Okay? Now, what if you have K being greater than 1? What happens when product is a bigger number than reactants? Well, what that means is that the reaction favors the forward direction. Forward direction. You're making products. Literally making products. If you're making product, that means this reaction is pretty spontaneous, isn't it? Hence, delta G will be a negative number. Just like what we looked at last class, this reaction is spontaneous. So whenever you calculate the fact that product is greater than reactant in this case, where Kc is greater than 1, hey, expect the reaction to be spontaneous, and of course the reverse process will be reverse. So if you have more reactants than product, obviously reactant favors, meaning that the reaction is going this way. Okay, reactant is favored. When that's the case, you're not making product. You're not. You're going to have a hard time trying to make products. So, this reaction is probably not going to be spontaneous. There has to be some sort of spark to get this to become this. If you get what I mean. All right. Let's take a look at a couple of graphs. These are actually in your textbook, so let me just kind of give you a clear rundown in terms of what they talk about, and then we're going to move on to some sample questions. So, when you see a spontaneous reaction, obviously delta G is less than 0. We mentioned that already, and they mentioned it here. What this graph is indicating, of course, is indicating entropy, the randomness of this system. And in a spontaneous reaction, as the reaction progresses, as you can see from this graph, that delta G will be lower and lower and lower. Okay, meaning it becomes more and more and more in terms of giving off using the Gibbs free energy. And there will be a point where it kind of plateaus off like we're mentioning here. Now, what's happening here is that this Gibbs free energy has decreased enough to reach what we call equilibrium. So this is equilibrium. This is when K is equal to 1. Now, if you look at where this is in the reaction progress, you can see that from reactants to product, this is more towards the product than to the reactants. So it's closer to the product side, meaning that this reaction right here is where it's product driven, it's product favored. Okay, being product favored, it is definitely spontaneous. And another thing that you can pick out of this graph is that if you look at the endpoint, the Gibbs free energy endpoint and its starting point, it's lower. Okay? It's lower. What that means is that energy has been released. Sort of, you can think of it that way. Okay? And nature's favor that. Nature favors delta G being less than 0. So, let's take a look at the same type of graph, but in a reaction that is non-spontaneous. So this is a non-spontaneous situation where you have reactants right here, okay, in terms of its Gibbs free energy. But when you take a look at product, that Gibbs free energy actually increases. What that means is that delta G is going to be a number greater than 0. There's an increase in Gibbs free energy. More energy is needed. Okay? And when you see where the equilibrium lies, this is where the equilibrium lies. So you look for that. You look for when the slope here, the instantaneous slope, whatever they call it, is 0. Okay? You look for that. And as you can see, going down from it, this point right here is more towards the reactant side, meaning that for this reaction, it favors reactants. We saw earlier, a couple of slides ago, that when you have a reaction that favors reactant, when reactant's concentration is higher than product, Kc is going to be less than 1. Sorry, Kc is going to be less than 1. When Kc is less than 1, the reaction is going to be non-spontaneous because delta G will be greater than 0. So it's a little bit of graph that you kind of want to know and understand how to read. Now, when it comes to entropy, okay, what can you say about the entropy? Well, whenever you reach this point or this point, entropy right now is at its highest. This is where the randomness of the system is the most. It's the most random. Okay, molecules is going rapids here because they're trying to accomplish a reaction. Okay, all right, enough of that. Let's talk a little bit about temperature, and then we'll move on to a serious example. As we said, or as you already know from last class, that delta G is temperature dependent. Okay, we saw an equation last class where we are asked to calculate delta G for a particular reaction. And you can see that temperature is definitely involved. When temperature increases, the chances of delta G being negative is a lot higher. Well, how do you relate equilibrium with Gibbs free energy? Well, let me present to you this equation. Okay? Which is the quantitative relationship between delta G and K, but remember, just like last time, T has to be converted to Kelvin. It has to be. Because if you think about temperature being degrees Celsius, there is a chance that that can be a 0, and that can be a negative number, and that can really throw off the whole equation. Okay? Let's do an example. I want to know what is the equilibrium constant. At 300 Kelvin for the oxidation of iron. Here's the reaction. Okay? Purposely did this, so therefore you get 1 mole of this, so it's easier to kind of look at. And what I've given you here is data, actual data from the CRC handbook, the IB constant booklet, where you have the entropy value for each of the participant and its enthalpy of formation value for each of the participant. Of course, these guys are going to be 0. I really don't need to show you this because you know why they're 0. So let's calculate K. So the equation here that I just introduced you to is that delta G is equal to negative RT ln K. If you want to find K, you're going to need to find delta G. So let's find delta G. Let's do exactly what we did last class. That delta G is equal to delta H minus T delta S. Okay, so let's individually calculate delta H and delta S. Okay, so delta H is equal to the sum of the product minus the sum of the reactants. This is pretty simple because of all those zeros. But remember those units. It was those units that really, snake people. Delta S, okay, it's going to be 1 times 90 minus 2 times 27 plus 1.5 times 205. Okay, that's going to be around 271. It's going to be rounding it off. Joules per Kelvin mole. Okay, now we're ready, okay, to find out what delta G is. Kind of ready. Remember, always remember, because a lot of people don't, is that delta S is measured in joules. You can't really apply it to this equation if it's not in kilojoules, because delta H is in kilojoules. So make sure, okay, that you divide delta S by 1,000. So that would be 0.271. Can't stress enough of that. Okay, so this is a number that is within interest. This is a number within interest. So let's calculate for delta G. So delta G is going to be equal to negative 822.2, okay, kilojoules per mole, minus the temperature here is 300 Kelvin. So automatically, for a fact that Kelvin is going to be canceled. Okay. All right. Here it is. I'm sure I'm missing some room here. Okay, let me just write it here. I'm just going to write out the answer. So delta G is going to be negative 743.1 kilojoules per mole. Okay? And hopefully you totally understand why. That is equal to negative R. Okay, so negative R is 8.31, okay, times temperature in Kelvin, that's 300, and ln K. Okay, now that means ln K is equal to, this is a negative 743.1 over 8.31 times 300. So ln K is 298. I hope I'm right. I hope I'm right. Actually, something's wrong here. I wonder if you know. Something is wrong here. What's wrong is that I might have not wanted to turn this into kilojoules. Yeah, I think it would have been better if I turned this into joules. Does anybody know why? I hope you do. It's because R, man, 8.31 is in joules. That's right, 8.31 is actually in joules. So, oh my goodness, it would have been better off if I actually turned this into joules per mole instead of turning this into kilojoules per mole. Because we're so used to kilojoules per mole from last class that, you know what, when you're trying to find out what K is, you're going to have to make sure that it is the same unit as R. All right, no big deal. It's pretty simple to do. All you have to do is multiply this by 10 to the power 3. Okay, that's when you'll get 298. The answer is still 298. Okay, the answer is still 298. It's just that I forgot about that. Okay, all right. Getting that out of the way. So what is ln K? Let's go here. So in this case, K is equal to E of 298, and that is 2.6 times 10 to the power of 129. Wow! Check out this number. This number is huge. This number is bigger than Avogadro's number. Right? What does that mean for this reaction? This reaction, the oxidation of iron, is never going to go backwards. Okay? At 300 K, which is pretty much close to SATP, this reaction is going to go forward. It's always going to go forward. Because K, look how big this is. This is huge. That means there's probably almost zero reactants. Right? You're going to have lots of these. So when this reaction occurs at 300 K, not only do we know that this is spontaneous, okay? Not only do we know that this is spontaneous, but we also know that you're going to get a lot of product. The product is going to be favored. You might as well just take this away and just do this. But no, of course, this reaction is a reaction where it can go backwards. It's just not in this situation. All right. Sorry for the mistake with the units. As I said, unit tricks me all the time too. Hopefully it doesn't trick you with this example. So what I want you to do is I want you to calculate for delta G this time, given the fact that this is your equilibrium constant for this reaction at that temperature. All right, we'll take this up next class. Bye, guys.